Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Unit 4 of our course on quantum transport. This is the first or the introductory lecture. Now, as you know, in the last 3 units, we have developed this general approach for quantum transport problems. The basic input is this H describing the channel, the sigma 1 and sigma 2 describing the 2 contacts. And if you have that, you can use these NEGF equations to calculate the current or any other quantity of interest like electron density, density of states, etc. And in general, you want to include the interaction with the surroundings through the sigma 0, but that requires a self-consistent calculation. Now, what we'll do in this unit is we'll talk about this problem involving spin transport, and we do it kind of with 2 things in mind. One is, this is a very interesting area where there's lots of activity at this time. And so it's an interesting problem in its own right. But pedagogically, it also gives you a good way to, get familiar with these equations, because it's the same basic equations that we'll be using. So it gives you some practice in terms of using the equations and interpreting results. Because basically the only difference, you see, when we include spin into the description compared to what we have done before, the only difference is, you see, when you didn't have spins, we had a set of basis functions. You see, if you had 5 basis functions, these matrices would have been 5 by 5. Now, the basis functions are coming in pairs. Like for every upspin basis function, there's a corresponding downspin basis function. So now you would have 10 basis functions, and so the matrices would be 10 by 10 rather than 5 by 5. So if it was n basis functions to start with, when you include spin, it's 2n basis functions. So in that sense, mathematically, that's about all that happens. On the other hand, there's an enormous amount of physics involved in how you write these matrices, the H's and the sigmas, and how you interpret the quantities you calculate, like G, N, A, etc. And that's what we'll be doing in this unit. So we won't talk too much about these interactions. Instead, what we'll consider is magnetic contacts, for example. That is, because a lot of the activity these days in spintronics involves manipulating spins through the use of magnetic contacts. And we'll talk about how, when you have magnetic contacts with the magnetization, this M1 and M2, how that information can be used to write down the sigma 1 and sigma 2 for the NEGF method. And also when calculating currents, instead of just the charge current, how you can calculate spin currents as well. Now, I should mention here that a very important phenomena that's getting a lot of attention in spintronics these days is the spin transfer torque. The idea that if you have a thin magnet here, like a nanomagnet, which means something that's say a few monolayers thick, then when the spin current is large enough, it can actually turn that magnet. And if you want to include that effect, then you need this LLG equation, the Landau-Lifshitz-Gilbert equation, where the input is the spin current and the output is the magnetization. But we won't be going into this aspect in this unit. So the idea is we'll treat magnets as fixed things. They have a certain magnetization, and we'll focus on the transport part of the problem. That given certain magnetizations, how you write sigma 1, sigma 2, how you calculate spin currents. Okay. So why are magnetic contacts important? Well, that's because it's a very important physical phenomena that has found widespread applications in spintronics, is this basic observation that if you have an ordinary channel, a non-magnetic channel with magnetic contacts, if the magnetization is parallel, the resistance is lower than what you get if the magnetization is anti-parallel. So how could you understand that? Well, one way to think about it is, supposing you had non-magnetic contacts, and let's say the resistance is 100 ohms. So the way you should think about it is this is a non-magnetic channel. So you got upspin channels and downspin channels. And you got contacts which have both upspins and downspins. So overall, it's almost like an upspin and a downspin running in parallel. And it's as if each one has a resistance of 200 ohms. But when you put them in parallel, the current is twice, the conductance is twice, and so the resistance is half. So what happens when you put a magnetic contact? Well, the idea is that the magnet gives you a good contact to the upspin channel, but a bad contact to the downspin channel. So the net result is this still stays about 200 ohms, but this becomes very large. And so the overall resistance now is doubled. It's like 200 ohms. What if you had anti-parallel contacts? Well, now you see you have a situation where for upspin channels, you have a good contact on the left, but a bad contact on the right, because this one is a blue magnet. Whereas when you look at the downspin channels, you have a good contact on the right and a bad contact on the left. So the net result is neither channel can conduct very well. And so the overall resistance gets to be large compared to this case, because in this case, one channel at least is, the upspin, the red channel is conducting very well. So this is the key point here, that usually, this is entirely an interface resistance effect. It is related to the properties of these interfaces. And the idea being that when you have a magnet that's pointing in, say, upwards, it gives you a good contact to the red channel, to the upspin channel, but a bad contact to the downspin channel. Now, why is that? Well, let me just say a few words here. That the way I think about it is, see, every electron is like a little magnet, although it's a quantum magnet with some subtleties, as we'll discuss. But it's like a little magnet, and this is an experimental fact that was discovered like almost 100 years ago. There's this Stern-Gerlach experiment, which showed that each electron had a magnetic moment. And this magnetic moment is 10 to the minus 23 ampere square meter, which is kind of like a 1 milliamp current loop running around the square of 1 angstrom side. And so you could think of this, every electron has a charge Q, but it also has a little magnetic moment. It's like a current loop, which is what you kind of think as if it's turning, as if it's spinning. But the experimental fact is that it has a magnetic moment. So why are most materials non-magnetic? Well, because there's as much upspin as downspin. So when you look at the density of states in the channel, or the number of modes, you have as many red states as blue states. And so when you fill them up, there is no net magnetization. And the same with non-magnetic contacts. Contacts have a lot more density of states, a lot more modes, but equal amounts of red and blue. But when you get to a magnet, because of these internal interactions, that's part of this physics of magnets, actually there is a lot more of one type of spin than the other. So a lot more reds than blues, let's say. So what that means is, when a red electron wants to get out into this contact, it has lots of states to get out into, and so this functions like a good contact. Whereas when a blue one tries to get out, there's very few states there, and so it doesn't function as a good contact. And so when you look at the red channel, you see it finds a nice contact. The blue channel doesn't, because the density of states is so low. So now the question is, how could we include this effect into the NEGF models that we have discussed? And for this discussion, you can assume a device that's just 2 points, and one upspin point and a downspin point. Now, real devices, of course, may have 10 points, but you can see the basic spin structure of what we are doing by looking at just 2 points. So if it's a non-magnetic channel, what it means is H will be a 2 by 2 matrix, and it's non-magnetic, so both upspin and downspin have the same properties, same epsilon, same energy levels. And so this is it. On the other hand, when you look at the self-energy in the context, you have to take into account the fact that electrons, up spins can get out easily, down spins cannot. And so alpha is bigger than beta. What about an anti-parallel contact, one that is pointing in the opposite direction? Well, now you could argue that the roles of upspin and downspin have been reversed. And so instead of alpha and beta, you now have beta and alpha. So this looks straightforward enough, that you got electrons of two types, the reds and the blues. And what the magnet does is it lets one type go out easily and the other type not so easily. Looks kind of simple and semi-classical. But there is an important subtlety, and that is, as soon as you consider magnets that are neither parallel nor anti-parallel but point in some arbitrary direction, then you see it's not so obvious what the gamma is like. So, and now you really need to get deeper into the quantum nature of spins, and how you actually think about spins and the subtle issues that are involved. And let me just say one thing in this context, and that is that in understanding spin, an analogy that is somewhat useful is that of polarization of light. Because what you learn in freshman physics is that light is described by this electric field which defines its polarization. And if you had a polarizer and an analyzer that are parallel, then the light flows straight through. But if they are orthogonal, 90 degrees, then it blocks the light. Well, you could think of this also similarly, that if the magnets are like the polarizers and the analyzers, and so when they are parallel, the electron flows smoothly, and so the resistance is small. But the important subtlety is that with light, you'd get the highest resistance if the polarizer and analyzer were at 90 degrees. But that's not true of electrons. You get the highest resistance when it's 180 degrees. And this is, of course, the key difference between the spins and the polarization of light. Polarization of light is described by vectors, which we learn in vector algebra, that if you have something pointing in some direction, it has these three components, x, y, and z, which you can write as, the z component is cosine theta, the transverse component is sine theta, and then sine theta cosine phi, sine theta sine phi, the kind of thing you learn in vector algebra. But when you are describing spinors, you visualize them the same way, as if it's pointing in some direction, but its components are given by these two complex quantities. And this is, of course, not at all obvious, and this is the kind of thing that we'll be talking about in the fourth lecture, and where this comes from. And note here that this is theta, and here you have half theta and half phi. And that is why you kind of need 180 degrees to get orthogonal, whereas with vectors, 90 degrees is orthogonal. Now, next we'll talk about the spin-orbit coupling. This is a very important, actually, a relativistic effect that it can be significant in certain channel materials. And these days, there's a lot of interest in channel materials that have spin-orbit coupling. And that allows you to manipulate and control spins for spintronic applications. And the basic effect is something like this. The basic result is that in a normal channel, you see, you have equal amounts of upspins and downspins. And if you looked at the upspins, there will be equal number of states going to the right and to the left. So let's say 100 of each. Now, magnetic channels, there's a lot more upspins than downspins. So you might have, say, 100 of upspins, 50 of downspins. Now, when you have a material with spin-orbit coupling, that's not quite magnetic. It's really more subtle. It's something like this. Now, if you look at it, you'd have, say, 100 spins going to the right, but only 50 spins going to the left. I mean, upspins. But when you look at downspins, the role is reversed. So overall, it's still 150 up and 150 down. But if you look carefully, here the 100 are going to the right, here the 100 are going to the left. So there is this asymmetry. So this is what's generally referred to as spin-orbit coupling. I guess you could call it spin-momentum coupling. That is, the states have their spins coupled to their momentum. That if you're going to the right, you have upspin. If you're going to the left, you have downspin. So these kind materials with these properties are now getting a lot of attention in the field of spintronics. Of course, our purpose here is to talk about how to include this into the Hamiltonian describing the channel and how to interpret results. And one important part of interpreting results is in terms of when you look at the device inside and you calculate, say, Gn at a particular point. I'd mentioned earlier that Gn is like the electron density, the diagonal elements. Now here if you look at a point, you'd get a 2 by 2 matrix. And you could interpret this upper one as n plus Sz as the number of upspin electrons. This one is the number of downspin electrons. And number of upspins is like n plus Sz over 2 and the downspin is like n minus Sz over 2. This you can see if you just take a simple example. Like let's say you have 75 upspins, 25 downspins. How many electrons? Well, 100. What's the spin? Difference, that's the 50. So you can easily see half of n plus Sc is 75, which is the number of upspins. Half of n minus Sc is 25, which is the number of downspins. So you can kind of understand where these diagonal elements come from using a simple semi-classical picture. What is not obvious is the off-diagonal elements, this Sx minus Isy and Sx plus Isy. And that's the kind of thing we'll talk about in the 7th lecture. That how this Gn, if you looked at it, it tells you not only the number of electrons at that point, but also the number of spins. And the point is the spin, it tells you the spin vector, not just the up and down components, that's the Sc, but also the transverse components Sx and Sy. And this quantity can be translated into a voltage. As you know, this number of electrons divided by the density of states tells you the occupation of the levels, which is like the electrochemical potential, as we talked about in part A. Similarly, the spin density, the spin accumulation can be translated into a spin voltage. And these quantities can be measured experimentally. So ordinary probes usually measure the local electrochemical potential. And these days, magnetic probes are routinely used to measure the spin voltage. And how you do that, those are the things we'll be talking about in this 8th lecture. And then finally we'll end with this idea of spin circuits, that you could, if you had a long device, then in general, let's say you had 3 points here. So overall it's like 6 things. So the matrix is like 6 by 6. But if you just looked at the diagonal blocks, then you'd get the number of electrons and the spin density at point 1, at point 2, and point 3. But of course, when you calculate using NEGF, you get a lot of other diagonal elements here. Question is, are those important? And these days there's a lot of experiments where those things don't seem to matter too much, because there are all these dephasing processes that destroy these off-diagonal elements. But just the information here is more robust. It's not destroyed so easily. And so it is important to look at this block and keep the off-diagonal elements, because that's where the spin information is. But you can get rid of the rest. And so you can have a simplified description where you don't worry about all these off-diagonal elements. You just keep track of the blocks. So at every point like this, you consider these 4 quantities, n comma s, or the spin voltage, or you can calculate this current and the spin current. And this gives you a simpler description overall involving, if there is 4 components at every point, rather than this overall this 4n squared components. So this is finding a lot of use in spintronics. And I like to talk about this a little bit also in the context that these might give you a paradigm for handling all kinds of other problems involving NEGF. Because NEGF gives us a general way of handling quantum transport. But the practical problem is once the matrices get too big it is practically not very easy to solve those equations. And so one good way to handle it could be that instead of keeping all these off-diagonal elements, you say that, well, we'll just take 2 of these and keep the off-diagonal elements here, but won't worry about off-diagonal elements between this one and the next one. And so, on the other hand, you might say, no, actually, we want to keep that one also. So you could take this whole thing and define that as a large spin, one with 4 components rather than 2 components. And in that case, of course, you'd need 16 things to denote the information there. Or you could include this one as well, all 6 components. Then you see 6 components for psi means like 36 components for psi dagger, for the GN. And those things could be useful for for problems that go beyond spintronics. But here, of course, we'll just end by talking about the spin circuits which are now being used to describe many phenomena in spintronics. So with that long introduction then, it's time to get on with the details. So we'll start in the next lecture with magnetic contacts and how you write down the self-energies. Thank you.